Hi, my name is Tomer, and this video is about the accepted SPAWC paper, Data Augmentation for Deep Receivers. I would like you to keep in mind a couple of points throughout the talk. First, machine learning is to be integrated into communication devices due to benefits that I'll discuss shortly. Second, supervised machine learning thrives in static scenarios where one can collect a sufficient amount of labeled data. So adapting ML to wireless applications requires novel adaptation methodologies that facilitate rapid retraining of the neural-aided components. So the contribution of this work is to formulate a framework that enriches a limited number of pilots with many more samples for retraining by exploiting the geometry of digital communication constellations. This is the agenda for this talk. First, we'll cover the relevant background, explaining a bit about machine learning for communication. Then, I'll present the problem setup, including the transmission protocol and the channel. Lastly, I'll explain what augmentations are in general and how we tailored the Augmentations Framework specifically to the detection domain. Data demands in 5G and 6G are only expected to grow. So to withstand strict standard constraints in terms of accuracy, latency, and complexity, we would like to optimize the components that compose the communication chain from the source to its destination. Let us consider the detection scenario presented here, focusing our review only on the transmitter and receiver components with a channel in between. Common channels nowadays are non-linear due to either power amplifiers and quantizers, and are quite complex as well with many interferences or jammers. In cases where we don't have the channel model specifically, or the analytical solution doesn't hold it anymore due to nonlinearities, one may desire to learn the channel mapping via some data-driven approach. But using machine learning in physical layer communication is different from usages in conventional domains, such as vision or speech. An assumption that machine learning makes is that the training distribution matches the test distribution. Obviously, this assumption is hard to make at many domains, and specifically at communication, where the distribution changes quickly as the channel varies. Looking on a simplified setup, let us consider a sequential transmission of blocks. Each block by itself is also transmitted sequentially bit by bit. The neural-aided receiver classifies the received channel values into the constellation symbols. The receiver is given by the mapping S hat, and its goal is to minimize the bit error rate over all transmitted bits and over all blocks. We consider a realistic scenario where the channel changes with time and the blocks are composed of pilots and data parts. The pilots part is short, on the order of tens of bits only, and is known to the receiver. The data blocks are longer, on the order of a few thousand bits, and are used for evaluating the retraining adaptation scheme. That is, we compute the bear from the previous slide only on these parts. Our goals are in general to find ways to retrain from short pilot blocks and from the longer data blocks as well. But in this work, I'll discuss the pilot part only. Another work that we did exploited the data part by an active learning scheme and was presented at ICASP this year, and you are more than welcome to check it. Going back to our approach, let us consider augmentations in general before presenting the proposed framework. A quick reminder is that augmentations are means to enrich labeled data with many more samples for some trainable model to train on. Each augmentation is a technique that builds on some partial knowledge of the data characteristics. For example, in image classification, one can use labeled image to generate multiple different images with the same label by rotating or clipping it. While data augmentation in general is common, it is still highly geared towards the image, speech, and language data. This motivates the study of augmentations that build on the specific domain knowledge. For communication, for instance, the geometry of these digital communication applications. The Augmentations Framework we propose takes the labeled samples from the current channel and enriches them in an augmented dataset, which is fed to some trainable receiver. To simplify the proposed technique, let us consider the QPSK constellation. Each colored point is a symbol on the constellation itself, as depicted on the transmitter side. After transmission through the channel, what we have at the receiver are the known pilots, that is, a few symbols from each class. Considering the geometry of the constellation and the physics of the channel, we can assume that outputs that correspond to the same input class tend to form clusters. So what we do is we fit some Gaussian distribution to the channel observations for each class. Then we can calculate each cluster first and second order statistics by averaging the class samples and measuring the deviation from the class center. Afterwards, we exploit this geometrical interpretation of the by-class clusters to generate additional class-specific data. This approach creates more reliable data for retraining of the neural-aided receiver, squeezing the juice out of the limited pilot observations. The framework must take into account a few principles that are important to the task at hand. First, the augmentation computation must be lightweight to facilitate online training. Here, we only need to compute 2 parameters per cluster and not a few millions of some GAN network. Second, the augmentation aids in avoiding overfitting on specific classes by sampling the same number of training examples from each class to train on. So to conclude this part, we suggested an augmentation framework that exploits a few pilots and the problem's geometry, taking into account real-time online training principles. To further facilitate retraining over time, we take into account the smooth varying nature of dynamic channels. Here we propose to average each cluster parameter over some window, incorporating previous estimated parameters into the current estimate. Moving to results, we consider transmission of a multipath fade-in channel with 4 taps that changes rapidly with the block index. The neural-aided receiver that we tested is Viterbinet, proposed by Schlesinger et al. On the linear Gaussian channel, we get an improvement of around 2.5 dB compared to regular training without any augmentations when transmitting 300 blocks, each composed of 80 pilot bits only and 5,000 data bits. I won't delve into the Gini-aided benchmark as they are fully presented in the paper itself. The interested case, of course, is the nonlinear one, as classical Viterbi fails on this one. Thus, a data-driven Viterbinet is the preferred option. Here, the nonlinearity comes in the form of a hyperbolic tangent on the channel output, simulating a saturated power amplifier at the receiver side. As you can see, smaller but consistent gains are achieved by our approach. So to sum up, we have seen an augmentation scheme that facilitates online retraining of neural-aided receivers, and we do so by exploiting the geometry of constellations and the smooth varying nature of communication channels. Please refer to our paper for more details, and you're welcome to check our published Python code on GitHub, and of course, the extended journal paper in the future. So to sum up, thank you for your attention.